make a quick announcement about order of events. So next week we have this class called Gyroscopes and Precession. We're going to do that today. And what's on the agenda for today is revisiting the Atlas machine, and we will do that next week. So the reason why we're going to approach the material on gyroscopes and precession today is because it's the sort of material that doesn't have, it is part of our curriculum, but it's not going to weigh heavily on like testing at all. And so it's a bit of an optional topic, and it's also a topic that is really, really interesting and also going to help us take a small step into kind of a larger mathematical world. And I think basically what I'm saying is, on a day where a lot of kids are out, I think this might be a better choice of topic. So, having said that, what we're going to do today is we are going to talk about torque as a vector. We will then see if torque's behavior as a vector is actually true. We will then see that it is true, and then we'll use that information to make some predictions about weird behaviors that are really deeply counterintuitive, namely gyroscopic motion and precession. So let me just remind you that when you deal with vector quantities in physics, you're dealing with things that have direction and magnitude. But it turns out that the math of working with vectors is not as simple as the math is working with numbers, right? So as you know, when we define work, we used this thing called the dot product, also sometimes called the scalar product, right? And the scalar product is a better name because it tells you what the quantity is that comes out of it, of the multiplication, right? So you can take the scalar product of force and displacement, and you get a number, not a vector, out of it. You get a scalar out of it. So work is not a vector, it's a scalar. Energy is not a vector, it's a scalar. So the interesting thing about the scalar product is that you're performing an operation with two vectors, which you're getting a number out. The other vector multiplication tool is called the vector product, and the vector product is the math tool that gives you a vector out of the operation, and that is what we're going to use to compute torque and actually pretty much every angular quantity. So I just wanted to cover a basic example of vector multiplication using the vector product, and then show you how that applies to torque.
Vector product is the same as cross product?
Vector product is the same thing as cross product. Yeah. So there's a couple of things that, before we even sort of talk about moment arm and force, I wanted to just make some general statements about the cross product and the vector product. So if you have two vectors A and B, okay, where you're taking the cross product of them, the magnitude of A and B crossed together is AB sine theta. Okay? And the direction is going to be perpendicular to both vectors that you start with. So for instance, if I say that vector C is the cross product of A and B, what has to be true is that vector C is perpendicular to A, and that vector C is perpendicular to B.
So if A and B were both, if A and B were perpendicular to each other, C would just like.
If A and B are perpendicular to each other, you need a third spatial dimension to compute A cross B. Okay?
Just perpendicular.
Yes. So and in fact, what Xander's just asked is the main way we will be using cross products and vector products throughout the school year. Okay. So this is the general idea. We have a way to compute the magnitude of the cross product, and then we have an expectation that the direction will be will meet these two about the vector product that are worth noting. A cross B is not equal to B cross A. Okay? In fact, A cross B is equal to negative B cross A. And this is obviously not the way regular whole numbers work, right? So the order of operations does not matter when you do A times B, right? But if you do A cross B in the wrong direction, you'll get the wrong answer, okay? So order matters when you're talking about the direction of a cross product, okay? Okay, so if we had a definition of torque as moment arm crossed with an applied force, okay? So as you know, we've been using torque as a magnitude expression of R, F sine theta. The other day we discussed things like projections of forces onto moment arms and projections of moment arms onto forces. That's what that magnitude with the angle thing is all about. We haven't discussed direction, and today we're going to use the actual mechanics of the vector product to find a direction. So allow me to show you how that works. When you compute a vector product, you are finding the determinant of this matrix. We put unit vectors across the top row. We put the first vector across the second row, which we're going to say is x, y, z, right? Components of the vector, x, y, z components. And then the final row is the x, y, z components of the second vector. So that would be f sub x, f sub y, f sub z.
And that's the determinant.
Put a vector in the entry of the determinant.
Pardon me?
You're putting a vector in like the entries of a matrix. I had J hat and K hat are negative vectors.
Yeah.
Is this just some notational trick?
No. So,
How, why do you put it?
okay.
Or maybe we'll be needed to that, so
Well, let me show you how this is going to work. So we are going to generate an I hat component that goes with the determinant of this subset. Okay. So we're going to say that the scalar multiplier that goes in the I hat direction is RYFZ minus RZFY. Okay? Let's say that again. RYFZ minus RZFY. Okay. The J hat component. Now I know that Ms. Lax has taught you in AT math to treat the J hat component as negative. But I'm going to do this slightly differently. It's a totally equivalent way. It's just the way that I've kind of thought about it over the years. What I'm going to say is we're going to take these elements and then imagine them as being over here. Okay? So I'm just going to say Rx and Fx down here. And then J hat is the scalar components of J hat belong to the determinant of this subset here. So we would say x minus Rxfz.
Or would that change the?
Well, because
because you're just flipping which one you
Yeah.
subtract and add.
right. So if you have seen this before in AT math, what you probably did was minus this, but flip those terms.
Okay, cool.
Okay.
Does it matter?
It's the same.
No, but
Nope, doesn't matter. All right, and then finally, we are going to be computing the K hat components as the Rx, Fy, Ry, Fx difference. Okay, so let me just take a moment here to say, you're never going to be asked to compute a cross product on an AP Physics test. It's likely that you'll be asked to compute a cross product on a homework set, but not on a test, number one. Number two, there is a subset of results here that we're very interested in as a conceptual tool, but the mechanics of this calculation is not really, it's not, the physics problems that are of interest to us don't rely on having this kind of expert ability to manipulate vector products, okay? The reason why I'm doing this is I'd like to demonstrate that this expectation of the direction of the result is true, right? And given this computation. So here's how we're going to think about that. I'm going to say that I have an x, y, at, yes?
Sorry, I still just don't get how you put a vector in like the entry of the matrix. 'Cause, like, in matrix, aren't the entries scalars?
There's nothing to say that you can't put vector elements in a matrix.
We literally put
Yeah,
all
we-
vectors.
all our vectors are vectors.
Copy, the P in copy is all vectors.
They're all
Yes,
the
but-
eigenvectors.
Oh, in columns?
In one entry. When in
Well-
P you have like there every single entry is scalar. You're just representing the vector as like a column. In here a single slot.
Does it matter to put a column?
You're dotting a single slot in the matrix. I mean you're like you're taking the determinant of a matrix that has entries that are scalars and vectors.
Okay.
So it's like a matrix across dimensionality.
Let me think about that. So it's possible that this is just a notational shorthand issue, right? Because
I'm just confused at
I could
what that would mean.
I could also say that vector r, I think that vector r is rx I hat plus ry j hat plus rz k hat, right? These would be essentially vector components. So I've just omitted the vector notation, right? And then when you do the computation here, the I hat essentially factors out, right? So I think so I'd have to like sit down and go through it, but the idea would be that, and you guys are probably more intimately familiar with this than I am because you're currently studying matrix mechanics and stuff like that.
Oh,
So I
wait,
like
wait, so it's like you're treating every entry as a vector.
Every
So
entry.
it's like a tensor.
It is actually a tensor.
No,
I guess all-
Okay, okay.
No, it doesn't work in this.
I just, yeah,
Happy.
okay, all right. No, but you're correct to notice that there was some notational.
That's good.
Okay, you're,
I'm making a note.
gotcha. So, let's do an example of torque calculation with the two vectors, moment arm and force, but really simple, like subset of what could be possible. So here's what I'm going to say. Let's say that you have a particle that is located on a positive x-axis. Okay? So I've got a particle located on a positive x-axis, and I'm going to be exerting a force on this thing that is into the board. Okay. So when I say into the board, I'm going to have to sort of try and draw this in pseudo 3D, which isn't going to be that challenging. But what I'll do to make that happen is I'll basically like say this. So let's say that I have a force like such, and that force is along the y-axis, which in my picture here is also into the board. Okay, so that's kind of a weird way to draw an XY thing, but the reason why I'm doing that, as you'll see, so what I've drawn here is sort of an outline of the geometric plane of x, y, okay?
So Z is
And
coming.
Z will be straight up on the page, as we'll see. But the question would be, like, let's say that this particle was attached to like a rigid massless rod and was constrained to move around that axle, okay? The moment arm would be the vector that connects the axle to the particle, all right? So there's my vector R, my vector F. This calculation becomes very, very simple if, as the way I've defined this, vector moment arm is along the x-axis, because it's got 0, 0 for yz components. All right, so what I'm saying is vector R equals R sub x, comma, 0, comma, 0. All right. Now, I've also chosen a very simple definition of a force, which is to say vector force is equal to 0, comma, F sub y, comma, 0. No component along x, no component along z. So now let's look at how the vector product gives us an answer that is purely along k hat, or the z axis. Okay. Ry fz, 0. Yeah. Rz fy, 0. Rz fx, 0. Rx, non-zero, fz, 0. Rx fy, that is non-zero. Ry fx, 0. So we have one remaining element along the z-axis. Okay? Interestingly, it's the magnitude of R and the magnitude of F. Okay? Directionally, if I were to draw this on my vector diagram, the answer is positive k hat. So let's draw that. That is the direction of the torque. Is the torque perpendicular? So torque is C. Is torque perpendicular to moment arm? Yep. Is torque perpendicular to applied force?
Yeah.
Yep. Okay.
What is torque?
Well, Warren, you are in the right place to have that question answered, because that is like the whole content of today's class.
Okay.
Yeah. So after class today, you should be able to answer that question in a lot of detail. Okay? So the simple answer is torque is a turning force, but that doesn't tell us a whole lot. Okay? I just wanted to label my coordinate axes here. Positive x, positive y into the board, positive z. Okay. There is an important shorthand for computing the direction of the vector product. All right? Like we said, the requirement is that the calculated thing is perpendicular to both vectors that go in, and the shorthand is called the right-hand rule. All right, here's how it works. Now, there's a lot of different permutations of this right-hand rule. If you're familiar with one that you're very comfortable with, please use it. However, I'm going to teach one method and not 19 methods. The one method I want you to follow is the following. Take your fingers, remember order matters, so you've got to put your fingers along the first vector, R. Take the right hand, point them along R. Then you curl your fingers into the direction of the second vector. And then your thumb points in the direction of the product. Okay?
Oh my god, it works.
So R crosses into F, points up. Okay? If you use your left hand, you will get negative B cross A. All right? So don't do that. If you use your left hand correctly, which you were pointing in the other direction for liver, right? Okay.
Oh, yeah.
So we've got, so let's just review what we've done so far. We've got a generic example of the magnitude and direction associated with vector product. Then we've got this very simplistic calculation of the vector product of a moment arm and a force that are along an x and y axis, giving us a torque along z. And you shouldn't be surprised to know that in any orientation of R and F, that the torque will be perpendicular to both of them. Okay? Okay. So then, Morgan's got a great question. What is torque? So what I'm claiming, right, is that if you walk over to the door, yeah, if you walk over to the door here, where there's an axle like this, and then the doorknob is here.
You're doing a torque upward?
Yeah. So the vector direction of torque is up when you open and close the door. So then, like, what's the point? Like, why would we, like, is this just like random math definition that has no basis in physics, or like, so it turns out that actually the torque really is up. And I'm gonna step you through the set of ideas and observations that will hopefully help you conclude that indeed there is physical reality to the vector product here. Because the thing we're gonna look at today, the gyroscopic forces in precession, cannot be explained otherwise. Okay, so they are a small thing in the world, but they're a very interesting thing in the world, and also there's like a lot of technological applications for having a good understanding of the physics of rotating things. So, before we do that though, I just wanted to pose like a question that maybe you haven't thought about yet in your thoughts on rotational motion. But back in the day, we said something like this. A rotating body, remember my ruler with the orange marks on it? We said something like a rotating body will have different linear speeds for every point as it rotates, but the same angular speed for every point as it rotates.
Yeah.
Okay, and that's not too complicated to understand because it's a rigid body, every particle is connected to the thing. Each one sweeps out the same angle, right? Because it's connected to this thing. But in order to do that, the speed has to get larger with radius, right? Because S equals R omega, V equals R omega, etc. Okay, so if I spin a wheel, like such, if I spin a wheel, every point radially has a different linear speed, and sort of as a vector, the linear speed for any one particle is constantly changing. Yeah? Okay. So if the linear speed is constantly changing, how, like, but the angular speed is not, and in fact, let's pretend for the sake of argument here that the angular speed is some constant value, like, oh, I don't know, 20 RPM or something like that. Can we think of a vector that describes the constant angular velocity, given that every single point has a constantly changing linear velocity vector? Is there a spatial dimension in this system that is constant as it rotates? And the answer is yes, it is the axle. Okay? Let's say it again. The only direction in this system that doesn't change as this thing spins is the axis of rotation. So if we are looking for a constant parameter to describe a constant thing, we have to pick the axle, right? Okay, so what I'm claiming is omega is like this along the axle. There is a right-hand rule for that. You actually curl your fingers in the direction of rotation, and your thumb points along omega. Now, here's why students like Seiji, for example, cannot wrap their mind around this. There are some things I won't say anything about, but Seiji is not one of them. Here's one thing about this that's really quite complicated. If I say to you the velocity of this thing is along the axle, you might be expecting that if I released it, it's going to move along the axle. But that's not the kind of velocity I'm talking about. We now have to be more careful about what velocity we're talking about. The translational velocity of the center of mass of this is 0. okay? The angular velocity does not give this translational displacement. So if I release this thing, it does not translate in the direction of the angular velocity. It continues to rotate in the direction of the angular velocity, which is along the axle. Okay, so, okay, let me just review that. The axis, so the axle is the only constant thing in this problem. The right-hand rule for rotation tells us that it's along my thumb. And if I let this thing go, it's not like it's going to have translational motion of the center of mass along omega. The only way I give this thing translational motion along the center of mass is to exert an unbalanced force on the center of mass. So here's like an example. If you spiral a football, okay, spiral a football, the football has both a translational velocity vector associated with the center of mass and an angular velocity around its axis. Okay. On the other hand, if you're spinning a basketball on your fingertip, that is pure rotation, right? Without translation. All right. So what is angular velocity? Because it turns out that torque, as the rotational equivalent of force, is going to create angular accelerations, and angular accelerations are going to grow angular velocities. Right, so then the question is like, what is angular velocity as a vector? And I just have to erase this.
I'm sorry, I was
Josh, it's okay. I asked Joshua to erase the boards because he arrived early. And now I'm giving him stink eye for only doing half of it.
You like erasing the same thing.
Where's this library?
Okay, so the question was, well, what is angular velocity? So I'd like to complete the picture of angular quantities. So, well, we're going to complete the picture of angular quantities. Do you guys remember back in the day that F was equal to ma? But then I said, nah, that's a bit simple. Actually, F is the timing change of momentum equals ma is a subset of this. Okay. Momentum is a vector. Momentum is a vector scaled by mass and parallel to velocity. Okay. There is an angular equivalent of momentum. It's called angular momentum. And the way we compute it is exactly how we computed torque. So to go from force to torque, we took the vector product of moment arm and force. To get from linear momentum to angular momentum, we're going to compute the cross product, the vector product of moment arm and linear momentum. We're going to give this thing a name. We're going to call it angular momentum. We're going to give it the symbol lowercase l. The magnitude of this is simply r and v. It's actually r and v sine theta, but let's just call it r and v for simplicity right now. Next week we'll address the whole sine theta thing. The direction of this is along the direction that is perpendicular to r and perpendicular to the momentum. We also have rigid body angular momentum. If there is an angular velocity omega, and we scale it by mass, we can expect an angular velocity for the body that we'll call capital L. Right? So angular momentum for particle, angular momentum for a rigid body. And finally, this F is equal to dPdt. I don't know if you want to take a stab at what the angular equivalent to that's going to be. What do you think?
So torque is equal to dl.
Yeah. The angular equivalent to this is torque is equal to dL dt. Okay, and I'm going to use for the particle. So it's also a vector equation. Remember, force is not in the direction of momentum. Force is in the direction of the change in momentum. Torque is not in the direction of angular momentum. Torque is in the direction of the change in momentum. Or actually, I think the better way to say that would be that the change in momentum of the system is in the direction of the force. The change in the direction of the angular momentum of the system is in the direction of the torque. Okay, that was a mouthful. I set out to answer Morgan's question, what is torque anyway? If torque is the cross product of moment arm and force, we would expect torque to be perpendicular to both moment arm and force. We need a way to measure that or observe that. If there is an unbalanced torque on a system, it will create a time rate of change of its angular momentum. Angular momentum, though, is really just scaled angular velocity. And what I mean is, it's like, as a vector quantity, it's just the vector that defines the axle in the problem. So if you have a net torque on a system, you could create a change in rotational rate, or you could change rotational direction.